turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello and welcome to The Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers from the worlds of science, technology and medicine. I'm Chris Smith, and coming up, scientists successfully treat Huntington's disease for the first time. They've slowed the rate at which it progresses by at least 75%, and we'll hear how they've done it. Also, the High Seas Treaty has taken a step closer to protecting the world's oceans, and the Earth-sized planet not that far away that might have conditions suitable for life. The inherited brain disorder Huntington's disease has now been successfully treated for the first time, scientists said this week. The illness destroys brain cells in a part of the brain that's called the striatum, which we use to plan ahead and make decisions and make movements. The condition strikes in early middle age and it leads to progressively severe disability. Hitherto, doctors had only a handful of drugs that they could use to control the symptoms to some extent, but the benefits were extremely limited. Now that has changed, thanks to a gene therapy breakthrough that's enabled doctors to dial down the activity of the defective gene that causes the condition, slowing the rate of progression to such an extent as Ed Wild, consultant neurologist at the National Hospital for Neurology and Neurosurgery at UCLH, and one of the team behind the breakthrough, puts it, it effectively means an affected person could achieve a normal life expectancy now.
What we have is a gene therapy which for the first time slows the progression of Huntington's disease by 75%, which is a result that wildly exceeds our most optimistic hopes.
What actually is Huntington's disease? How does it affect a person? And how do they get it?
So it's a genetic brain disease caused by a single mutation in a gene that's a recipe for a protein called Huntington that is produced in every cell in the body, but it's particularly harmful when it's found in neurons. The presence of this mutation causes this protein to build up gradually over the years. Eventually, the neuron can't cope with the harm that the protein does, and so it malfunctions and dies. What that translates into clinically is a really, frankly, horrible brain disease that typically comes on when a person is in their 30s or 40s. Patients slowly lose their ability to control the movements of their body. They lose the ability to walk. They develop involuntary movements. There's a form of dementia. It's not the same as the sort of forgetfulness of Alzheimer's disease. It's more of a sort of higher level functions like multitasking, loss of ability to recognize emotions in other people. But that becomes very, very severe. And eventually patients end up bedbound and unable to communicate. And there's more terrible news for people from HD families, which is that a person with the mutation, each of their children has a 50% risk that they will inherit it. And as of 2 days ago, it was an untreatable condition with no treatments to slow it down.
And what's been your approach to get on top of the problem?
For roughly the past 10 years, we've been focusing on a group of treatments collectively aiming to reduce production of the abnormal protein. So it kind of makes sense to say, well, why don't we try and switch off production of the protein? We've been testing a gene therapy, and the impressive results that we've finally been able to share have been in the context of this new experimental gene therapy.
So talk us through how that works then. What's the approach? How do you get the gene therapy in? Where does it go? And when it's in there, what does it do?
So the gene therapy is a harmless virus called AAV. Basically had all of its content scooped out and replaced by a designer strand of DNA. It couldn't be given as a pill or as an injection into the vein. It has to be injected directly into the substance of the brain in a lengthy neurosurgical procedure. So we're talking 12 to 18 hours of brain surgery, a few small holes drilled in the skull, and then tiny plastic tubes called catheters are passed down under guidance from an MRI scanner so that the drug can then be injected directly into the striatum, which is this bit that's particularly vulnerable. Once the virus is injected, That's it. The person recovers from surgery, and then no further intervention is required in most cases. But what's happening inside the brain is that the virus has injected its cargo of DNA into the neurons, and it stays there. It's an extra gene, essentially, that stays there for the rest of the person's life. And that's why it's a gene therapy. That extra little bit of DNA tells the cell basically not to make the Huntington protein. So it's basically tagging the Huntington message molecule with a flag that says, delete this, we don't want to make this protein. And what we are sharing now with great joy is the result of 3 years of treatment in a group of patients who have undergone that procedure.
How many people have you tried this on, and over what period of time have you followed them up? You say 3 years, but is that 3 years of follow-up, or over 3 years you've been doing this and now you're beginning to follow them up?
So yeah, we're looking at 3 years of treatment from around about 30 people, of whom 12 received the gene therapy at the high dose. So it's not a large number, but the size of the effect is so huge that it ends up being of kind of undeniable statistical and human significance.
How do you know it's actually working, though? Because if it's stopping a process, how do you know what would have happened to a person had you not intervened?
It's a very important question. And what we would normally do to answer that question would be to enroll a placebo arm, and people would be randomized to active treatment or treatment with a dummy pill or injection. You can't do that with a gene therapy, it would be unethical. So, what we've had to do is compare the people treated in this trial with a group of around 900 people that were taken from a much larger study that's just an observational study. In other words, it's a study that's following how Huntington's disease progresses without involving any treatment. That gives us a very accurate impression of how much we would expect these people to progress. And then we're able to compare where they actually are at 3 years versus where we would expect them to be.
Were there any negative effects? I mean, you are putting into the brain a foreign virus, albeit a disabled one. The immune system might have something to say about it. Did everyone do fine, or were there any people who had problems? Or do you foresee any potential threats or risks or things we need to think about before you roll this out more broadly?
Your question about inflammation is a really pertinent one. In a minority of patients, roughly 10%, there was a slightly unexpected delayed inflammatory reaction. So, about 2 to 3 weeks after the virus was injected, a small number of patients ended up experiencing initially mild headaches, in some cases, some confusion. And when we looked at those brains on the scan, there was an unexpectedly large amount of swelling. So that's probably just a bit of natural variation in the strength with which people's immune systems act when they encounter a foreign substance like a virus. The good news with that is that the most that was needed to bring that under control was symptomatic treatments and some short-term treatment with anti-inflammatory steroid drugs. And it was really gratifying that after the early inflammation resolved, there haven't been any later side effects or anything major emerging.
Did the patients and their families notice that things have stopped deteriorating, and how do they react?
They really do. And it's been striking for me as well. I've been looking after HD patients for 20 years. I'm fully prepared now. Whenever I see one of my patients, they'll be worse off than they were the previous time. The disease will inevitably have progressed. And that's simply with my patients in this trial, they basically haven't really changed in the 3 years since they were treated. They were walking at the start of the trial and they're still walking now. One of my patients had to take medical retirement before the trial, and he's been able to go back to work. He's honestly my only HD patient who's ever been able to go back to work. So the numbers are impressive, but behind the numbers are these sort of personal stories of people for whom the experience of having Huntington's disease has been quite significantly different from what it would be expected to be.
Some absolutely wonderful news, and I'm sure very welcome news, for Huntington's disease families. That was Ed Wild at UCLH in London. A landmark deal to protect the world's oceans is about to take effect. The UN's High Seas Treaty, which has now been ratified by dozens of nation states, will formally become international law in January. Its ambition is to reverse the damage to marine life and to safeguard vast areas of oceans that lie beyond any national borders and are currently very much a maritime Wild West, where pretty much anything goes. Protecting this vast expanse safeguards migration routes and it preserves important, poorly documented ecosystems like the seafloor. Here's Callum Roberts, who's Professor of Marine Conservation in the Centre for Ecology and Conservation at the University of Exeter.
International waters represent such a large chunk of planet Earth. They occupy 61% of the surface of the ocean and 43% of the surface of the Earth. And until now, they've been a roughly half planet-sized hole in our conservation policy. There's been no legal instrument available that we could all agree to abide by to protect wildlife on the high seas. And that's been a real problem because there's a lot of industrial activity taking place on the high seas, like industrial fishing, which is causing immense impacts to wildlife.
I was just going to say, what are the major threats? Is it just fishing? Because that's the obvious one. Are there other things that conservationists are worried about?
Well, there are direct and indirect threats. And of course, climate change is the indirect threat, which looms over us all, and it looms over international waters just the same as land. So that's putting pressure on wildlife there. Of course, there's another looming potential presence in industrial terms in international waters, and that is mining, deep sea mining. This is immensely controversial. It would be enormously impactful. The impacts would be impossible to reverse on any kind of human timescale.
So now a significant number of countries have said they're going to abide by the rules. But what about the ones that say they won't then? Does that mean that countries that haven't signed up are still just going to go and do whatever they like?
Well, countries can, in theory, do what they like if they're not signatories to an international treaty. You don't have to abide by the terms of that treaty if you haven't signed up to it. But on the other hand, it would be deeply divisive for the world community if some countries decided that they were going to go in and exploit waters that other countries had decided should be protected. We can see, looking back at Japanese whaling in Antarctica, that there was a huge amount of international opposition to that. And eventually the Japanese decided that it was creating too much diplomatic strife and they stopped whaling in Antarctica. I think we would see the same kind of thing, that countries that haven't signed up to the provisions would hopefully at least abide by them in terms of, let's say, a protected area was established. They wouldn't go in and exploit that protected area.
Has China signed it?
China has signed, but not yet ratified.
Well, what's the difference between ratifying it and signing it?
Well, signing it is an indication of intent, and in some cases, let's say a small island state, the signing and the ratification are almost the same thing. A head of state will have the power to essentially do both. In other countries, though, principally democracies, the parliament has to agree in a formal process that the country is going to abide by the provisions of the treaty, and that process is called ratification. China is obviously one of the huge international maritime powers. Its fleets of fishing vessels, for example, are among the most pervasive and also destructive of marine life in international waters. So it's very important that China really does ratify this and agree to abide by the provisions of the treaty.
Are they showing signs of doing that yet, though?
I am not entirely sure about that. Of course, America hasn't ratified the treaty. It has signed as well under the previous administration. I think the Trump administration is fairly hostile to the High Seas Treaty at the moment, and Trump himself has signed an executive order trying to persuade companies to go forth under the United States flag and start deep sea mining. So I'm not overly hopeful that under the present administration they will be very supportive of the High Seas Treaty. But on the other hand, they're not signatories. They haven't ratified the United Nations Convention on the Law of the Sea, which came into force in 1994. Yet they have abided by the provisions of that treaty, more or less in whole, as a kind of traditional law.
So let's take the rose-tinted view that everyone does abide by it then. What does this translate into now? Now we're over this threshold. What does this actually mean in practical terms?
Well, this is a huge opportunity to establish protections for wildlife on the high seas, and that includes ocean-going tunas that cross entire oceans during their migrations. It includes whale sharks, manta rays, seabirds, that whole panoply of marine life, which is undertaking large-scale movements in the international waters. Those animals are essentially coming into the crosshairs of industrial fisheries in many parts of their ranges, and they're being depleted. Many are becoming endangered. The High Seas Treaty gives us the tools to create internationally recognized marine protected areas to safeguard their populations. And this is really important because the world has committed to establish 30% of land and sea as protected areas. In the ocean at the moment, the headline figure is that we've passed about 9% of the ocean protected. But if you look at how that's subdivided, 22% of national waters of countries are protected, whereas only 1.45% of the international waters is protected. So there's almost no formal marine protection given to the high seas, and that's something which we must rectify with extreme urgency.
So if you've got migratory species, for example, they might be well protected in one jurisdiction and they might go to another extremely well protected jurisdiction, but making the journey between the two through the high seas, they would fall prey potentially without this sort of treaty. Is that the point you're making?
That is the point I'm making, and they will still fall prey in some parts of the high seas unless we were to close it all, which is a recommendation that myself and other scientists have made recently. But assuming that in part we can protect the area of international waters, then there are hotspots of biodiversity and richness. There are concentrations of marine life feeding on other marine life. If we protect these, the highways and the crossing points, then we can afford disproportionately large amount of protection to species for a relatively small area that's actually lying within those marine protected areas.
Well, it sounds like mostly good news, doesn't it? Let's hope that the US and China do come aboard too in due course. Callum Roberts there at the Centre for Ecology and Conservation in Exeter.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith. Still to come, the Earth-sized planet not that far away that might have conditions suitable for life. But first, paracetamol is a safe and effective medicine that's been easing headaches, soothing fevers and taking the edge off pain for more than half a century. But this most trusted of household products has now been dragged into a political debate in the United States following a claim by the Trump administration that the agent causes autism. I asked Ian Douglas, who works on drug safety at the London School of Hygiene and Tropical Medicine, to tell us what's going on, starting with why guidance hitherto has been that paracetamol is the safest anti-inflammatory drug to take if you're pregnant.
Over the years, there have been several studies in different countries, in different populations, where people have tried to look at whether paracetamol exposure in pregnancy is linked with autism. And these kinds of studies are incredibly difficult to do because the women who receive paracetamol in pregnancy are fundamentally different from women who don't receive paracetamol during pregnancy. So, for example, they may have long-term medical conditions that mean that they are more likely to need pain relief, or they might have a fever or an infection during pregnancy, which leads them to need to take paracetamol. And we know for sure that things like infection during pregnancy or fevers, they themselves can be associated with a cause of an increased risk of autism in the children of those women. So we know that those women are fundamentally different and that they will definitely have a higher risk of children with autism than women who don't take paracetamol. But it's not because of paracetamol itself. So when people do these studies, they have to do the best they can to adjust away those differences between women who do take paracetamol and women who don't. And that can be incredibly difficult to do. It's the bread and butter of the work that I do, so I know it's very hard to do. But one of the studies, in fact, the most recent large study that was done on this was done using Swedish data last year. They did something really clever where they actually looked at siblings. So brothers and sisters whose mothers had taken paracetamol during one of the pregnancies, but not during the other. And there was no difference in the risk of autism between the pregnancy where paracetamol had been taken and the pregnancy where it hadn't.
Paracetamol is an over-the-counter drug, though, and therefore a lot of these studies are going to rely on self-reporting by the patients. So how reliable and how robust are data like this, so that when we draw conclusions like there's no link, we know we can rely on it?
That's a great question. And you're absolutely right. So these kinds of medications that are available over the counter are notoriously difficult to study. And so people will do things like they'll do structured questionnaires, they will interview people and do the best they can. But even then, we know that the data won't be perfect. And again, this Swedish study that was done last year, they went to great lengths to look at if they were to get the exposure status wrong, so if they were to just not really know how much paracetamol people were using, how badly would they need to have got that wrong in order for them to have made an unsafe conclusion? And it looked like the degree to which they would have had to get it wrong would have almost been implausible.
Therefore, the reassuring message emerging from that study that you've just outlined is that it's business as usual. If you're a pregnant woman and you need some kind of painkiller, you should stick to business as usual. Paracetamol is, as far as we know, safe in pregnancy. But where did Donald Trump come by the information that led to the dramatic announcement he made earlier this week then?
Honestly, I don't know why. It's a really great question, and I wish somebody would answer it.
I mean, I did a bit of poking around myself. I found one study that came out relatively recently. It was in the journal Environmental Health, but it wasn't actually doing what the Swedish people did that you just described. It was basically taking every study under the sun that had ever been done, massing the whole lot together in what's called a meta-analysis to get data from about 100,000 people and considering that as one giant study. And they did find, they claim, a small increase. But that isn't doing it in the discrete, well-controlled way that the Swedes did. So do you think that's where the error may lie?
You're right. So the systematic review was done earlier this year, and they concluded that they looked like there may be a small increased risk, but they, I think, were quite clear that they couldn't be certain that it was a causal risk. So again, to me, it seemed like, yes, you've amassed some of the information and put it together, but it wasn't concluding there's a causal increased risk. And the other interesting thing for me is that even if you look on the US FDA, their drug regulators' statement about this, even they are saying we haven't shown a causal association. So to my mind, these messages, they don't warrant the more political message which came out early this week. So I don't see where that link is coming from.
What really concerns me is that, and I think many people share this concern, is that about 20 years ago, we saw the same sort of thing happening with the MMR vaccine. And even though there was no evidence and people have gone to enormous lengths to reassure people, it's still in the front of any concerned parent's mind when they're asked, are we going to be vaccinating your child with the MMR? And it's done enormous damage to the image. And do you think that there's a real danger here that a woman who's pregnant may find herself thinking, well, I better not take anything because there might be no smoke without fire, and it leaves pregnant women in a worse situation and potentially in a worse pregnancy situation because any inflammation or pain or ill health in the mother in pregnancy has got to be worse for the developing baby?
Unfortunately, I'm absolutely sure that you're right about that. And as well as untreated illness during pregnancy, the other thing that concerns me is that because the spotlight is now unfortunately on paracetamol, it's quite possible people might look around their homes and think, well, I've got some ibuprofen, for example, lying around. Maybe I'll take that instead, which we know for sure is not safe during pregnancy. So it's the law of unintended consequences that also concerns me around what will people do instead.
So, bottom line, sticking with paracetamol is the agreed current best practice. That was Ian Douglas at the London School of Hygiene and Tropical Medicine. Into space now, and groundbreaking new research suggests that TRAPPIST-1e, which is an Earth-sized planet about 40 light years away, might have an atmosphere, a crucial ingredient for habitability. Using the James Webb Space Telescope, scientists have ruled out thick hydrogen or CO2 atmospheres, leaving open the possibility of a thinner, nitrogen rich blanket, much like the one surrounding our own planet Earth. More observations are planned to unravel the mystery of this tantalising exoplanet. But what have we learned so far, and how? Well, here's Ryan MacDonald at the University of St Andrews.
So, what we are seeing when we look at TRAPPIST 1e is potential signs of air, what we call an atmosphere on this planet. So, we're seeing bumps and wiggles in our data that are best explained by a nitrogen rich atmosphere, similar potentially to our own Earth, which is 78% nitrogen. We're being cautious at this particular stage. We need more data in order to confirm what we think we're seeing. But what's incredibly exciting here is that this could be the first exoplanet in the habitable zone, a rocky world that could have air. And that has huge implications for the search for life.
What's the habitable zone?
The habitable zone is the distance from a star where it's not too hot or not too cold to have liquid water on the surface.
So Goldilocks would feel very at home there.
Yes, Goldilocks will be very at home in the habitable zone.
How did you actually image that atmosphere, though? How do you know there is air there?
We stare at a star and we wait for the planet to pass in front of that star. We call this a transit. And when this happens, a small amount of light from the star filters through the air on the planet, if indeed it has air. And what we're trying to do is look at how different gases that are present on the planet absorb different colors of light differently. For the same reason that plants are green and not red or some other color, molecules, gases do the same thing. So we use this technique, which we call transmission spectroscopy, to map out which particular gases can explain these tiny little dips where light from the star is missing.
Does it matter what colour the star is? Because stars come in different shapes and sizes, colours, and heats. So is there an optimum for doing this? And does that constrain what you can and can't look at with this technique?
Absolutely. So the star TRAPPIST 1, we call it a red dwarf star. It is about 10 times smaller than the sun. And as you might guess from the name, that means it's quite red instead of a yellowish star like our own sun. We've chosen to focus on red dwarf stars specifically because they're smaller. It means that more of the light from the star is blocked by an Earth-sized rocky planet, which makes it easier for us to make these measurements and search for an atmosphere. It's not all easy though. Red dwarf stars are kind of horrible. They have eruptions on their surfaces that we call stellar flares. So it's still very much an outstanding question whether or not life could actually exist on a planet around this kind of very violent star that's quite different from the sun.
Given that this is very much remote from the Earth, and you can tell us perhaps how far it is in a second, how do you know how big the planet is?
So the star system here, TRAPPIST-1, is about 40 light years away from Earth, so about 10 times further away than the nearest star to us, but still, a ridiculously long way away. And so we can measure the size of a planet by seeing what fraction of the star's light is lost when the planet passes in front of it. A large planet will block more light than a smaller planet, and that's how we know that a planet like this is about the size of the Earth and not like Neptune or Jupiter.
We know that life got started on the Earth very, very promptly, didn't it? We know the Earth's about 4.5 billion years old, and we've got signatures that might point to life from as early as 4.1 billion years. So therefore, it doesn't necessarily have to be an old system to have life. Does it look like a mature system, this TRAPPIST system?
Yeah, the TRAPPIST-1 system is not a young system. It's been around for billions of years, so there's plenty of opportunity potentially for conditions to evolve on the world and potentially for life to emerge if there's anything along the timeline that we see here on Earth. The problem, though, is that the planets will have experienced different conditions over time, and it very well may have been that when the star was young and was even more violent than today, it could have stripped away all the gases around the planet. And that's why we're trying to establish, is it a bare rock or is it a planet with an Earth-like or Venus-like atmosphere? And so this is really the frontier of exoplanet science at the moment. Which rocky worlds have atmospheres, which have air?
Given that you can see an atmosphere, can you infer anything about the density of that atmosphere? Because we know that the conditions on the Earth are ideal to give us the conditions that favour life here. So, can we read anything into the fact you can even see an atmosphere around that planet?
If we see an atmosphere on a rocky planet many light years away with the Webb telescope, it immediately tells us that this atmosphere has to be thicker than a planet like Mars, for which we just wouldn't be able to see an atmosphere. It's not dense enough. So, whether or not the atmosphere is a hospitable pressure, like we have on Earth, or a much thicker atmosphere like Venus, that requires additional and more sensitive observations.
Can you get at that with the technique you've got, the tools at your disposal? Now you're beginning to be able to make measurements like this, because this is a first, isn't it? It's the first time you've really been able to nail a problem like this. Can you interrogate this further to begin to point to what the conditions might be like on that planet?
One of the key things that we're trying to do to understand the surface conditions is by measuring which chemicals, which gases are present in the atmosphere, because the Earth would be completely uninhabitable without the greenhouse effect from carbon dioxide warming up our world. So we want to see if we can detect gases like carbon dioxide and measure how much of the atmosphere is CO2. We can then use that to calculate what the surface temperature would be, and hence if liquid water could exist, which is crucial for the potential habitability of worlds like TRAPPIST-1e.
I'm put in mind of interviewing the singer John Anderson a few years ago about his recollections of the Apollo moon landings, which interrupted a concert he was supposed to be giving. And he recalled to me, thinking at the time, what a wonderful time it is to be alive, as the astronauts stepped out onto the lunar surface. And it really is amazing to see this new frontier of exoplanet science now unfolding in front of us, isn't it? That was Ryan MacDonald. He's at the University of St Andrews, talking about their observations on the far-off world TRAPPIST-1e. Well, sticking with space science now, it's time for Question of the Week, and we've had quite a few of you get in touch with us about our recent programme on gravitational waves. Over to James Titko.
Thanks, Chris. Gravitational waves are the ripples in space-time predicted by Albert Einstein, emanating from the interactions of massive bodies like black holes or neutron stars. Scientists have been able to detect gravitational waves from billions of light years away using laser interferometers here on Earth. As mentioned, our show on this topic sparked a lot of questions from our audience, and the first one we're going to tackle is this.
Hello, Naked Scientist. Paul here from Toronto. Related to your show on gravitational waves, how is the energy conserved so well that we can detect gravitational waves here on Earth from interactions of massive bodies on the other side of the universe?
Thanks, Paul. Brilliant question. Would the energy of gravitational waves start to diminish so that we could not detect them by the time they reached us? I put it to Ben Alanak, Professor of Theoretical Physics at the University of Cambridge.
The energy released by, for example, the collision of two black holes is absolutely enormous. For example, in the first measured gravitational wave, where two very quite massive black holes coalesced into one, it's inferred from the data that about 3 times the mass of the sun was converted into energy and released into gravitational waves. So that's enormous. So that's why you can measure it with a very sensitive measuring device such a large distance away. That combined with the fact that the experiments are so sensitive and can measure change in distances of the space or change of stretching of the space to 1 part in 10 to the 17.
So you're right, Paul. The energy of gravitational waves, like all forms of radiation, dissipates over large distances. We just need sensitive enough instruments. This was evident in the first detection of gravitational waves, where the merger of two black holes 1.4 billion light years away caused the LIGO laser to shift by a distance smaller than the width of a proton. Thanks for that. For our next question...
Hi, this is John Bondi from Vermont in the United States. My question is, do gravitational waves also experience a red shift just as light waves do? Can we measure the shift as we do with light with emission and absorption lines? Thank you.
Another lovely question from John. Redshift refers to the increase in wavelength of electromagnetic radiation, like light, travelling to Earth from the most distant objects in the universe as it expands. As you say, we can use spectral features, like absorption lines on a colour spectrum from red to blue, to measure how much the wavelength has changed. But does the same apply to gravitational waves? Back over to Ben Alanak for the answer.
Gravitational waves do experience redshift, just as electromagnetic radiation, such as light, does. You can't use emission or absorption lines, though. Electromagnetic radiation has that because it's produced in atoms, which, because of quantum mechanics, gives you discrete choices for the wavelengths depending on which atom it is and so on. But you don't have this in the gravitational setup. What you do instead is you try and work out which galaxy the gravitational wave came from. And if you can find that, you can find out what the redshift of that galaxy is, and the redshift of the gravitational wave will be the same because it'll be equivalent from the point of view of the expansion of the space-time.
So, John, the wavelength of gravitational waves increases as they travel across an expanding universe, just like light waves do. Unlike light, however, they don't have emission or absorption lines that we can use to measure the redshift directly. We may be able to infer it, though, by comparing it with electromagnetic signals from the same event. Thanks for those brilliant questions. If you'd like to keep the discussion going, why not join in on the thread on this topic over on nakedscientists.com/forum. Next time on Question of the Week, we're answering this one from Bhavesh, voiced up by a member of our team.
How do guided missiles reach their targets?
And do be sure to keep your questions coming in. It's chris@thenakedscientist.com. No question is a stupid question. They're all an opportunity for discussion and debate, so do please send them in. That's it for this week. Do join us, though, on Tuesday when we're going to be looking at the role of chemistry in painting. The Naked Scientist is supported by Rolls-Royce and by all of you who chip in to help support our production efforts. You can do that if you wish to, and if you do enjoy the programmes, do please consider doing so over at our donation page. That's at nakedscientist.com/donate. I'm Chris Smith. Thanks for listening, and from us here at the Naked Scientist team, till next time, goodbye.